these particles, these problems used to be a lot more emphasized in calculus books when I first started teaching calculus, but now they're not so frequently occurring. But it has something to do with what they call rectilinear motion, where you're moving in a line like a car. Now, if you're going to be a civil engineer, you're going to be studying traffic patterns, and you will be studying rectilinear motion because you study traffic and you try to figure out how to time the lights on the traffic systems. And so you need calculus to do the rectilinear motion or the traffic flow. But this is the idea. This is what's happening here. We have the time axis. And imagine there's a particle, a car or something, and the particle is on the axis. And the particle has some force on it. And in fact, it has velocity. And with the velocity, it's going to move. Positive velocity will move it forward. Negative velocity will move it back. A zero velocity means it's stopping. It's like you hit a traffic jam and your car stops. You get zero velocity. And then the traffic clears up. Or maybe there's an accident, so you have to go backwards. You have negative velocity because you're backing up. Or you get it. So this particle is moving back and forth, depending on the force on it. And all we know about the force is the velocity function. Okay, so having a sense of understanding the velocity will help us understand what the particle is doing. Now, we have some context here. We're not going to look at everything. We're only going to look at the time where we're going to start observing the particle at 1 second. And I don't know which way the particle is moving. Now, theoretically, you don't need a picture at all. If you understand the net change concept, the fundamental theorem, you can do this problem without a picture and come up with a good result. But the second part, I don't think you will be able to do that without understanding the velocity and how it's impacting the particle. So what I want to do is just kind of get some intuition, what's happened to the particle. And it's influenced by velocity, and I don't know what the velocity is doing. And I'm going to use a strategy from chapter 4 on sign analysis. I want to analyze the velocity. So let's see. Critical numbers happen. This is position. So the derivative of position is velocity. So velocity is going to give me critical numbers when it equals 0. I'd like to know those numbers. And it turns out this is factorable. T minus 3, t plus 2 equals 0. Okay, so I have two critical numbers, a positive 3 and negative 2. Okay, now negative 2 isn't really relevant to us, but it is cool. We're going to still need to analyze the signs for the different time numbers. So I'm going to do a sign chart just like we used to do. Velocity, time, and I have negative 2 was a critical number, and I have 3 is a critical number, and technically I'm not going to have negatives, but time is in this interval because I have a time of 0, I have a time of 1, which falls in this middle interval. And you remember this, I hope now. We've got two factors. Each of these factors will tell me whether velocity is positive or negative. So I'm going to do the first factor. And when time is bigger than 3, like 4 minus 3, this is positive. And when time is smaller than 3, like 1 minus 3, this will be negative. And I don't need this for time smaller than negative 2 because it's out of my domain, but I'm going to complete the table just for closure here. Next was the other interval. I'm sorry, not interval, but the other factor. So when time is bigger than 3, like 4 plus 2 is positive. And when time is smaller than 3, like 1 or 0, 1 or 0 plus 2 is still positive. And smaller than negative 2 is negative, but that's kind of moot here. So the times that I'm interested in are 0 and 1. Oops, I'm going to put those below. This trademark. Okay, so this is the part of the velocity that I'm most interested in. Now, if it made sense, which it doesn't, for time below 0 seconds, I'd have a velocity that's a negative times a negative, which is a positive. So if we could conceive, or if it made sense in some weird physical context of time negative 2 seconds before I began, the velocity would be positive, which means the particle would have been going forward. Okay, now, between 0 and 3, what's the velocity? Well, this factor is negative, and this one's positive. And negative times a positive means here, the velocity is negative. And then after 3, positive times positive is positive. Okay, so when we start at 1 second, the velocity is negative. If the velocity is negative, which way is this particle going?
Backwards.
It's going backwards. It's in reverse. So it's hard to draw rectilinear motion because rectilinear motion is only, two-dimensional back and forth. But we'll cheat, and we're going to go backwards. And we're showing our particle moving backwards for a little while. Okay, now, the particle is going backwards. Does it go backwards forever? What happens at 3 seconds?
Goes forward. Goes forwards.
Well, you're on the right idea. If you put in 3 here, 3 minus 3 is 0. The velocity equals 0. So it was going backwards, but it got slower and slower and slower. And at the 3-second mark, velocity of my particle hit 0. And then if you go bigger than 3, like 3.1, this will be positive and this will be positive. And then the velocity is starting to go positive. So now it hits 0 and the particle is actually turning around. Okay, so this would have happened here at t equals 3. That's the turnaround point where the particle changed directions. And we're going to go a little further. Now, we don't know. Actually, I know because I did the problem. But if you were drawing this, you wouldn't know. Does the particle stop to the left of my starting point, or does it keep going beyond and stop over on the right? You don't know. You don't know until you find the displacement. What is the displacement? If I start here and end here, this is the displacement. This is my drive, where I drove. It's kind of flipped, though, of my drive. My drive, I went forward for a while, and then I went back. And so I'd be left with this little bit. This particle went in reverse for a little while, and then it went forward. So this is where the ending position is, and this is where the starting position is. And so that little piece is displacement. That little piece is net change. Because I have some positive going back and some negative going forward, I add them up. I add the positive and negative, they cancel out, and what's left is my displacement, just like this. I have some positive above and negative below, add them up, and this is what's left over. It's the net change. All right, that's the big idea of what's happening. Now, the sign analysis, we didn't need this picture to do part A. We could just say, okay, as long as you understand displacement means net change, and net change is an integral. We're going to go from, we're not going from 0. We're doing this domain here, 1 to 4 of the velocity. And if you integrate the rate of change, you get the net change of position. That's what we're doing. So this equals the integral from 1 to 4 t squared minus t minus 6 dt. That's going to be t cubed over 3. That's going to be minus t squared over 2 minus 6t. We're going to evaluate from 1 to 4. And the rest is a lot of basic math. Well, let me show you 2 levels of doing this problem. So let's put 4 in here. I don't have room for all of that. So 4 times 4 is 16 times another 4 is 64 thirds. 4 in here is 16 over 2 divided by 2 is 8. And 4 times 6 is 24. Okay, that's f of 4 minus, and I'm going to put 1 in, f of 1, big F of 1, that's 1/3 minus 1/2 minus 6. Now, I want you to give me exact answers as often as possible. How do we get an exact answer for that guy? Use your calculator. Don't give me a decimal, because a decimal can often lead you into a round off, and then you don't have the perfect answer. But let the calculator do it for all these fractions. So 64 divided by 3 minus 8 minus 24. Close that group. Minus a new group. 1 divided by 3 minus 1/2 minus 6. I'm going to close the second group. Make sure I typed it all right.
You don't need a parentheses in between like the fractions?
If you have multiplications and fractions, it's good to use lots of parentheses with your fractions. But I think here the calculator knows the order of operations well enough that it will know to do 1/2 first, then minus the 6 later. But if you have doubts, what Hunter is suggesting is with fractions, be very generous with parentheses when you're doing calculator math with fractions. Just so if you have suspicions, yeah, put your fractions inside of parentheses also. But I think we're going to be okay with this. And down here, I want you to pay attention to this button, the math button. It's 1, 2, 3, 4 down. The math button has a menu command, and the very first item in the menu of the math button says convert my answer to a fraction. And so it's going to take that long math problem, and it's going to give me an exact answer as a fraction. So I didn't know it was going to come out like that, but now I do know. And it's hard to read in the calculator, but it's -9/2. So this is -9/2 meters, because we were doing meters per second. So the displacement is finishing on the negative side. So the net effect is this particle went back from here to here. That's the net outcome. You just forget the whole story and what happened in the end. It went backwards 9.5 meters or 4.5 meters. That's the net of the story. The particle went backwards. If this had been positive, then that would have meant the end of the story is the particle finished over on the other side. It went back and then came forward and ended up with a little extra positive. Okay, that's the first question, displacement, we got it. Okay, let's do the second question, part B. Second question is find the distance. Now with distance, we don't talk about negative distance. Net displacement, we would have positive and negative. With net area, we're going to have positive area and negative area. But if we want total area or total distance, we're going to make it all positive. So in this picture, if I wanted the total area, this picture, I could not use a negative number for it. Let's say this one is area 1, area 2, area 3. If I want the total area, a total, I would take A1 plus A3, because those are already positive. But what am I going to have to do to area 2 to make it give me a total area? I'm going to have to multiply it by negative. Because area 2 is already a negative number. So a negative times a negative will make it positive, and then I'll have all positive areas to add up. You guys following my logic there? Does that make sense? Any questions? So we're going to do a similar idea to the particle because we want the total distance. You remember my story when I went to Zion? For those 2 hours, what was my total drive? I drove 75 miles, and then I drove back 25 miles to meet my son. Well, the net drive was only 50 miles. The 2 hours, I'd only made 50 miles of progress. But my total distance was 75 going out plus 25 more going back. So my total drive was 100 miles in those 2 hours. And now we got to do something like that here. Because this particle, it had a distance going backwards and a distance going forwards. So we're going to have to make both distances positive. And so that's going to require the absolute value function. So here we go. If I want total distance, we're going to have to do the absolute value of velocity. Okay, so now, part of the time, this part of the time, it's already positive. I've got positive forward moving distance. So from 3 seconds to 4 seconds, my velocity is moving me forward, so I'm going to have a positive distance to take account for. But that's not true from 1 second to 3 seconds. From 1 second when I start, my position was going negative backwards. So I have to make that a positive number. So when I integrate from 1 to 3 of my velocity, this integral is going to have a negative answer. That's why this came out negative, because this first part of the journey was mostly negative, canceled out that little bit of positive, and so I had a negative answer. I don't want this to be negative. So what do I do so it won't come out negative?
Oh, Mr. Eckert, isn't the integral thing from 1 to 4?
Yes. But if I do 1 to 4, I'm just going to get this answer again, because I'm going to have some negative canceling out that positive. And so it's just like doing this integral. If I just do the integral from 0 to 2, I'm just going to get this negative 0.6 again. I have to make sure that the negative parts of the integration aren't negative anymore. So I got to force them to be a negative times a negative and make it positive. And I know this part of my journey from 1 second to 3 seconds is the time I was going backwards. So how do I make that distance come out to be a positive number distance?
Multiply by negative.
Times it by a negative. Now, on the next part of the journey, from 3 to 4, I'm moving forward. So from 3 to 4, I'm already going to have a positive distance. So I don't need to mess around with from 3 seconds to 4 seconds. So I can leave this part alone. Okay, that is important to see how I broke that down. It's going backwards here. So my backwards would give me a negative answer if I integrate. And I don't want it to be negative, so I'm going to take the negative answer and times it by a negative, so this will now be a positive number. And this part is already positive. So in order to keep the whole thing positive, I had to make the negative portion become positive, and I left the positive portion stay positive. Okay, so let's integrate. The antiderivative of velocity is right here. I've already done my work. And I do have to be careful because on these guys, they're negatives. I'm making a negative of that answer. So let's put t cubed minus t squared minus 6t. I'm going to evaluate this from 1 to 3, but I'm going to make that answer negative. Plus, I got this one. Now, the integral of velocity is, we've already done the work. It's going to be that, except my bounds are 3 to 4. So this is going to be t cubed over 3 minus t squared over 2 minus 6t. And my bounds on this one are 3 to 4. Okay. The calculus is done. The algebra was figuring out this absolute value thing. The calculus was easy. It's just the antiderivative. So there was algebra here to set up what's happening. Then we did the calculus and we got this, and the rest now is just algebra and basic math. Now, let's use the calculator here because there is way too much basic math. But if you set that up for me and I saw that on your paper, then I would know that you understand what you're doing. And so if you did the rest with your calculator and showed me the final answers of those steps, I'd like to know what is this answer and what is that answer, and then finish that off. So how can we do that in the calculator? In the last problem, I showed you how to do it in the calculator where we had a whole bunch of them, and we could repeat this strategy. But since I have to do this formula and this formula with 1 and with 3 and with 3 and with 4, it's the same formula, except this one's going to be negative. There's a lot of plugging in, and I don't want to do all of that work. So I want the calculator to do more work for me. So I'm going to show you another strategy where we can employ the calculator for all of this. Remember, this is negative, but this part and that part are the same. I'm going to put this formula in the calculator. And I can't use t's, though. I have to use x's, so I'm going to do x raised to the third divided by 3. Oops. Divided by 3. Then I have minus x squared divided by 2. And then I have minus 6x. Okay, so I want to double check. Did I type it in right? X cubed divided by 3, x squared divided by 2. Yes, okay. So this calculator has y1 memorized. My y1 is our formula. And I want to plug in 1 into this y1. I want to plug in 3 into this y1. I want to plug 4 into this y1 and get those answers. So let's quit second mode, and that gets me to my home screen. Now, in order to do this new strategy, I'm going to use something called the variables. The button is called vars. Vars is short for variables. So I click on vars. And there's a lot of different things we can set up in our variable menus, but the one we want is y variables. So I'm going to go sideways to the y variables. Now, what we know is functions. When you go to Math 280, you'll learn about parametric and polar functions, but we don't know those yet. We just know algebra functions. So it's already highlighted. I'm going to hit enter, and there's all my y's. Now, my y1 is the one that has my memorized formula. So I'm going to hit y1, hit enter, and it puts it on my home screen. Now, I want to plug 3 into it to do the fundamental theorem, and it's just like big F of 3. You put 3 in parentheses. I'm going to do big Y of 3. Oops, forgot the parenthesis. So this is just like F of X, F of 3, big Y of big F of 3. I'm just doing Y1 of 3 minus vars button, grab Y1 again, and plug in 1 this time. And there's the fundamental theorem right there, all worked out. Now, I also want an exact answer. So I'm going to go to the math menu and tell it, okay, give me a fraction, so I'll have a perfect fraction answer. Now, I'm being a little tricky here. Remember, this is supposed to be negative. I didn't do the negative. This is my distance going backwards. And when I get it, I get a negative distance. I get negative 7.3 meters, but I don't want that to be negative. I'm not counting the negative distance. I'm counting it as a positive distance so I can get my total. So I take that negative times this negative, and I get 22/3 for this problem. Now let me pause. Is everybody okay? Any questions? Anything on there that doesn't seem right or is confusing or we want to clarify? Well, we're hitting break time fast. The hard work is done. So now I want to do the second integral from 3 to 4. Well, I can arrow up, grab the previous command, put it on the command line, and now I'm going to edit the command line and put in 4 to 3, hit enter. And the second part of the journey was 17/6. So the particle went 22/3 meters backwards, and it went 17/6 meters forwards. I'm adding both of those numbers together. Now this one is not positive, but so I'm gonna add that one plus the 22/3. Math it out, and the total distance is 61/6 meters. There's a perfect answer, exact answer. And if I wanted to decimal round off, it's about 10.2 meters. So the total distance the particle was moving, we go take all the backwards distance and all the forward distance, was 10.2 meters. But the displacement is the net change. When the whole story is done, we started here, ended here, and that means we were backwards 4.5 meters. All right, so there we go. We got this application done.